Ben. So it is my pleasure today to introduce Professor Ed Maginn. He is joining us from Notre Dame. Unfortunately, he's literally joining us from Notre Dame because we're still virtual. He got his undergraduate, some background information, his undergraduate degree from Iowa State, his PhD from Berkeley. He then took a somewhat non-traditional track, I guess, and went to Procter & Gamble. I didn't get a chance to ask you about this, but it sounds a little different than a typical path. And then after this stint at Procter & Gamble, got his position at Notre Dame, and he's been there for a little while now. He's worked up through the ranks to be a full professor, and he's now a named professor, the Keough-Hesburgh professorship. He's now at a point where he started earning fellowships, and so he's become a little a little famous. He's a fellow of the American Institute of Chemical Engineers, the American Association for the Advancement of Science. He works on the board of a number of journals. So if you're publishing in this area, you've probably seen his name, maybe at the Journal of Physical Chemistry and some other places. I became aware of Ed, and kind of the reason why he's been on my radar is I've been working for quite a while now looking at computational methods related to thermodynamics and molecular behavior of materials, and how can you take molecular information and extract this stuff. And I guess what really made me want to invite Ed, if there are any undergraduates here paying attention, is that a lot of the papers that come out of his group are really well written. Like, a lot of people can write papers, but it's hard to write a paper that's really well written. And so, I don't know, maybe for the last 15 or so years, papers that have come out of your group have been kind of guideposts for me to understand the literature and dive into it deeper. And in particular, his group has been working on problems related to phase transitions and how can we understand the phase that a material would be, particularly with respect to liquid-solid transitions, and then also with ion dynamics. So how do charged particles move through the condensed phase? How can we understand from the molecular scale the behavior of these sorts of systems? So his group has done a lot of really seminal work in these areas, and you should look up the papers. They're really well written. They're interesting reads. They're worth diving into. So please join me in welcoming Ed. Thank you for being here.
Well, thanks a lot, Garrick. That's a very nice introduction, and I really appreciate your comments. We try to write papers that are clear. It's hard to do sometimes, but thank you very much. That means a lot to me. I will start off by just introducing the topic, and it's sort of this. I haven't given this talk before, so I'm trying this out on you guys, and I'll show you some things that are not published yet, some new work that we're working on. But in general, I want to talk about how we can understand thermophysical properties of charged fluids using molecular simulations. And I want to take you back to ancient history when people started simulating molten salts, and then talk very briefly, not much at all, about work that we did for over 20 years on ionic liquids, but how that got us then to look at molten salts with fresh eyes, and back again to some other problems involving electrolytes. So as Garrick said, I'm from Notre Dame. I have to give you an obligatory 2 slides on what Notre Dame is. So we're up here on the southeast tip of Lake Michigan, right on the Michigan-Indiana border. This is 2 aerial views of our campus. This is the football stadium. We have a football team. We're getting USC is coming in town to play this weekend. So already there's some USC fans milling about, but it's kind of cold here, so they're suffering a little bit. But our building, where I am located right now, is right about in this area here, and there's some other engineering buildings here and in here. It's a nice campus. It was founded in 1842 by the French, so it's a Catholic university, fairly small, about 13,000 or so students, very high graduation rate. We have students from all over the country and the world. And this is our department. We're a fairly old department, started in 1905. And we organize ourselves into 4 distinct areas: soft matter, nanomaterials, energy and sustainability, bioengineering and medical diagnostic devices. And then the main area I work in is molecular simulation data science. But of course, we all work across multiple areas. So a lot of what I do is energy and sustainability. We've got about 100 PhD students, about 240 undergraduates, and you can see our faculty here, 23 tenure track and 3 teaching faculty, and we're hiring several more faculty. So if you're interested, graduate students, postdocs, We have a couple of different ads out. We're also very much interested in recruiting graduate students. We have an information session coming up in a few days online, which you can find at our website, cve.nd.edu. So I encourage you, or you can talk to me. I can tell you a little bit about our program. I think it's a nice place to do your graduate studies. So I'll tell you about molecular modeling of materials. And the most fundamental way you can do that is through solving the time-dependent Schrodinger equation, which I show here. And what I'm showing here is a picture, molecular representation of a single ion pair of an ionic liquid. This happens to be a cation, this big molecule that's an imidazolium cation paired with an anion that's PF6. And you can run quantum calculations on small systems like this. And if you want to do very accurate calculations, you're limited to a fairly small number of molecules or ions and very short timescales. So I can get things like structural or vibrational frequencies. I can get things like electronic charge distributions. Here you can see for this ion pair, red is negative charge, blue is positive. So I can kind of see how there's charge transfer between these ions. So I can learn a lot about these systems, but I'm in chemical engineering and we care a lot about bulk properties. And there you really can't simulate large enough systems or for long enough timescales to calculate those. So we need a way, and the reason for that is that this equation is too time consuming, too expensive to solve for many times. So we need to do a coarse graining and get a simpler representation of the energy that we can evaluate very fast, because we need to evaluate billions of energy calculations on large systems to calculate the kind of properties we want. So what we need is what's called a classical force field. And there are many ways that you can represent these energies of materials classically. Here's kind of the standard way that people do. They, instead of solving the Schrodinger equation, they parameterize things like the bond stretching frequencies to a harmonic potential. The same is true for, say, bond angles. You can think about a cosine series to represent the energy distribution for rotation about central atoms. Maybe you represent intermolecular distance energies with a repulsion dispersion function that looks like a Leonard-Jones type potential. And I showed you this electronic charge distribution. What you could think about doing is placing partial charges Qi and Qj on top of each atom and just using Coulomb's law to represent the electrostatic energies. And I won't say more about that, but this is a very important element in being able to calculate properties and get the right answer. And we spend a lot of time worrying about this. Ideally, you could derive these force fields from quantum calculations, accurate quantum calculations, and develop these parameters in a so-called bottom-up way. People also do a top-down way. You could think about finding experimental data and sort of tuning these parameters until you can match that. And we do both of those. The advantage of simulations then, of course, is that we can look at the simulation and understand what's happening at the molecular level. So here's an example of if I knew the potential energy from a force field of the atomic configurations, and I took the negative gradient of that, that's just the force if I want to treat my system classically, like with Newton's equations of motion. And so F equals ma here, I can solve that by taking very small time steps and propagating the equations of motion. And you can build little movies of your molecules moving around. So this is ibuprofen, and there's actually water molecules solvating it, but I'm not showing you those. And this molecule will dance around according to this particular potential energy and form a deterministic trajectory. And if I record those positions and the momentum of each atom and then apply statistical mechanical concepts, I can calculate really all of the thermophysical properties of that particular system. I'm not doing chemistry, I'm not doing reactions, but I am seeing how all these molecules move around, and so I can do thermodynamics and I can do transport properties. You can also use a technique called Monte Carlo, which is different in that it's stochastic in nature. And I won't go into the details, but you still need to know the energies of these configurations. But instead of following Newton's equations, you just make random moves of the molecules and accept or reject them with a given rule that guarantees that you develop a trajectory that has the right probability density. So this shows you kind of stochastic moves of molecules. They don't move as smooth like a movie, but you can still get these kind of sampling and get all the thermodynamic properties of your system, but you don't get the dynamical properties. Okay, so that's all I'll say. These are the two methods that we use in our simulations. We try to develop accurate energies. And now let's see what we can do with these methods. So I said I was going to tell you about ancient history and molten salts, and this is back a long, long time ago. People developed potentials for or energies, if you will, these potential functions that treated the behavior of alkali, halides, and salts in general way long ago, back in the 1930s. Mayer and Huggins did this, and then Tosi and Fumai, who were at Argonne at the time, back in the 1960s, developed parameters for all of the alkali halides that form a rock salt type structure. And they did that based on properties of the crystalline materials, which they knew. And they proposed a model that has this Coulombic potential I mentioned before. Instead of a Lennard-Jones potential, it has an exponential repulsion term, and then 2 r to the 6th, r to the 8th dispersion terms that are attractive. And you can look up this paper, and the parameters are in here. And these are just spheres now. And so you can go ahead and plug those into a simulation, and you can run calculations and figure out the properties of these salts at high temperatures. And in fact, when these potentials came out, that's exactly what people did. So some of the very first molecular simulations that were ever run were run on molten salt systems. Here's a classic paper from 1971 by Leslie Woodcock, who was at University of London. And he simulated liquid sodium chloride, or molten sodium chloride. And this is just some pictures from that paper. Here's what's called the radial distribution function. What this is the relative probability of observing 2 different species at a given distance. And here's the distance listed here. This is really in angstroms. And what you can see are peaks and valleys. And what this tells you is that for curve A, for example, the cation and the anion show a preference to locate next to each other about 2 angstroms apart. A totally uniform distribution of separations would be at a G of R of 1. So everything bigger than 1 tells you have an enhancement in the local density. And this just tells you the first solvation shell or coordination shell of where a plus and a minus would tend to orient in the liquid. And then you see a depletion, because after you see a plus and a minus, you see another plus. That plus plus is this curve B. So at a distance of around 3.5 angstroms, you have a plus and a plus separated by a minus. And then you can see this repeats. So this is just the alternating structure of a plus minus plus minus plus minus in a liquid phase, and it dies off at very long distances for liquid structure. And more or less, this is actually the liquid structure of liquid sodium chloride. So Woodcock got this right in 1971. They had a little more difficulty getting dynamics. So this is an attempt at getting diffusion coefficients. They're calculating the mean squared displacement, and they simply couldn't run these simulations very long. This is just for femtosecond timescales. So you need to take very small time steps when you run these simulations, and the computing power wasn't quite enough for them to really get diffusion coefficients. But this was really the earliest simulations, and people were interested in trying to model real fluids that were tractable, for which they had decent potentials. And then it kind of stopped. After the 1980s, there was some excitement about molten salts for different applications. People looked at all the kind of standard ones, and then this became unfashionable to look at them, and they sort of died off. And so for a long period of time, no one really looked at these. I'll show you, when I got involved as a new professor, I thought that this was really old fashioned, and we got excited about something called ionic liquids, which are different. But now there's been a renewed interest in molten salts. And the reason for that is now people are making high quality experimental measurements of some of the properties. We now know a lot more about these systems. And what we've realized is that the early simulations were not very accurate. They were problems with the system size, the time scales, the methods that they use. We now have much better methods. And so people are coming back and looking at these. And I'll show you that there's really good motivation for this from a practical standpoint because of reasons to get to zero carbon energy sources. I mentioned ionic liquids. This is what I'd spent most of my career working on for over 20 years. And ionic liquids are also molten salts. I showed you a picture of a cation anion pair here, but this is what a molten salt ionic liquid looks like. This is one of my graduate students' hands, and it's at room temperature, it's still a liquid. There's no solvent, there's no water. This is a pure salt that happens to be liquid at room temperature. And I first learned about this from a CNE News article back in 2000. And it was just fascinating to me that you could have a salt that was liquid at room temperature. And the reason that they're liquid at room temperature is because these cations are very asymmetric and the charge is delocalized over a lot of atoms. So they don't pack together very well, unlike a spherical sodium and a chloride. And so the melting point tends to be very high. These things will melt, or I'm sorry, very low. These will melt at minus 20 degrees C or something like that. And they remain liquid up to decomposition temperatures, and they have very little, essentially no volatility. So we started simulating these, and the nice thing is that the simulations were started at about the same time that experimentalists dug in. And so the field really developed as a nice partnership between simulations and experiment. And I think we contributed a lot to helping understand how these things behave. So much so that in 2010, when we published this paper, we had designed a class of ionic liquids on the computer, predicted their properties for CO2 capture. They were subsequently made experimentally after the fact and showed to perform the way that we wanted them to. And this led to a patent. And we actually formed a startup company that commercialized some of this. So this took about 20 years. It was a really good story of how simulations can help you learn something. But I'm not going to talk anymore about ionic liquids. But if you want to know something about that, I can answer some questions later. But this is what got me involved in ionic systems. And so now I want to tell you why I'm motivated to look at molten salts. And you've all seen pictures like this in the past. I wanted to, maybe you haven't seen this, to look at what happened when COVID struck to our CO2 emissions. And this is a really interesting plot of emissions in billion metric tons of CO2 from fossil fuels. And what you can see plotted here over 120 years is the steady rise in emissions. And there are all these world events that happened: the Spanish flu, the Great Depression, World War II ending, all the oil shocks in the late 1970s and early 1980s, the 2008 financial crisis. And these make little tiny blips in this trend. But the overall trend is pretty clear that it's a tremendously increasing function. And then COVID hit and the whole world shut down, and it did drop CO2 emissions substantially. But it didn't drop it to zero, and it didn't even drop it below 2000's level. So the emissions in 2000 were lower than what they were in the height of shutting the whole world down due to COVID. And this is going to pop right back up again. And I think if we look at it in 20 years, it's going to look like one of these small little blips. So that tells us that we can't just do this by trying to slow things down. We need a lot of effort to really reduce greenhouse gas emissions. And you can see here that electricity and transportation and buildings account for about half of the US global warming or greenhouse gas emissions. So you may have heard a lot about electric cars, and transportation is a big factor of this. And electric cars are great, but electric cars by themselves will not reduce greenhouse gas emissions. And the reason from that is that you need to get that electricity from someplace. So this plot shows you the grams of CO2 emitted per kilometer of travel distance in your electric car by energy source. And these dashed lines are the high and low values for gasoline powered cars. So what you can see here is if you get your electricity from coal or oil, you basically have the same emissions profile as a gasoline car, sometimes even worse if it's with coal. If you get it from natural gas, it's much better, but it's still not zero. And it's not even that much better than a really efficient gasoline powered car. It's only when you have really zero or very low carbon power sources like solar, nuclear, or wind that you can really drive down your emissions. And so we need to have those type of energy sources. And of course, we need to have good energy ranges. We need lots of cheap energy. We need this to be on the grid. This has to be cheaper than fossil fuels. So batteries are going to be key, and nuclear could be key as well. So the first thing I'll talk about is why molten salts. And we got involved in this because the Department of Energy is now thinking about sponsoring, or they are actively sponsoring, the development of the next generation of nuclear power, which are called molten salt reactors. And you can see that there are 3 different big companies that are also involved in the development of this. One of them is sponsored by Bill Gates, TerraPower. And the idea here is that instead of a conventional solid core nuclear reactor, you instead dissolve the fissile material in a molten salt and circulate that in the reaction. So there's a molten salt core, and then you have a secondary molten salt that's the heat transfer fluid. So you don't use water as your heat transfer medium, you use a molten salt. And there's many reasons why this is beneficial. You can run at much higher temperatures than you can with water. One of the big worries about moving to an all-electric economy is that we need tremendously high temperature process heat to run a lot of chemical processes like ammonia synthesis, even in production of steel, things like that. And you don't get that from solar or wind, but you can get that from a nuclear reactor. There's much safer than water-cooled reactors because there's essentially no vapor pressure of a molten salt. There's also passive emergency cooling. If this overheats, there's another molten salt plug that will release the core, dump the core onto the ground. It solidifies. It's contained now. It doesn't get released into the atmosphere. So there's a whole lot of reasons why this is interesting, but we need to go back and look at these molten salts again. People stopped working on them in the 1980s. We don't really understand the physical properties of those. We don't understand interfacial properties, corrosion, the solubility of different species. So I'm part of an Energy Frontier Research Center called MC, the Molten Salts in Extreme Environments. And you can see the partner institutions here. And we're interested in providing a fundamental understanding of molten salt bulk and interfacial chemistry. So we're one of 2 theory groups, the other's at the University of Iowa. And so I'll tell you a little bit about how we do these simulations now. So this is a different model from that simple Tosi-Fumai 1964 potential. We have basically the same structure as that old-fashioned potential where we have a Coulombic charge, a repulsion, and a little fancier dispersion attractive terms. But then we also add a polarization term here that includes charge dipole, 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 and an induction terms. That allows you to account for polarizability. So this is called the polarizable ion model, or the PIM. And Matthew Salon and Paul Madden and others have spent a lot of time developing this model. And it works pretty well. And it's more expensive, however, than this because we have to solve for the dipole self-consistently every single time we do an energy evaluation. So it's about 10 times more expensive than this fixed charge model or the rigid ion model. And so we wanted to kind of put this through its paces and see how it performs. And so in this paper here, JChem Phys, Haimeng Wang and my group did a lot of very detailed calculations using very rigorous methods, was very careful about statistical accuracy, system size effects. If we have time, I can tell you a little bit about how you have to correct for system size for diffusivities, how you have to do very careful calculations to get the viscosity right. I can tell you a little bit about how we did that, but we were very painstaking in how we did that. And we got benchmark values for both the PIM and the RIM model, and then compared that to the best experiments out there, which are shown as these red lines. And what you can see was kind of surprising to us is that both models do a very good job of getting the density, the viscosity, and the self-diffusivity of these different molten salts. The PIM does a little bit better for some of the salts, in particular in getting the density right. But it's for being 10 times more expensive, it's not that much better than the rigid ion model, which was a little bit surprising. For multivalent ions like magnesium chloride, which I'll show you some examples of that, the rigid ion model doesn't work and we need the PIM. But we did a lot of benchmarking studies here. We also calculated ionic and thermal conductivities. Very few people have calculated these properties, but they're essential for obviously in a molten salt reactor. And here you can see the results are a little bit more mixed. Our thermal conductivities, we tend to overestimate those compared to experiment. The rigid ion model sometimes does better than the polarizable ion model. Sometimes it does worse for the ionic conductivity. So these are what you can do with these simple models in calculating these important properties. And we can apply these techniques to a wide range of different molten salts. Garrick had mentioned that we're interested in solid liquid coexistence, and I'm very interested in this, and as well as vapor liquid coexistence. And so we set out to calculate the liquidus line between binary molten salt systems. And so just to remind you, your phase behavior, here's the temperature versus composition. This is the overall composition. Below this solid line, everything is solid. Up here in this region, everything is a liquid with composition dictated here, going from pure KCl to pure lithium chloride. And then these lines here are the boundaries, the liquidus curves that separate the liquid mixture from pure KCl and a liquid mixture having this composition. And this point is the eutectic, the lowest melting liquid composition before it becomes a solid. So what we can do is we can do a very simple direct coexistence simulation. We can take a crystal material, so in this case, pure KCl or pure lithium chloride, and put it in contact with a liquid of different compositions here. The overall composition is Z, and the liquid composition is X, given by these values. So these are all at the same temperature. And if I just let this simulation run, what should happen is I should start to form more of a solid. And if my model is right, I should eventually end up on the liquidus curve at that particular temperature. So that's what we do. We run a bunch of simulations starting at different compositions. We let them reach equilibrium. We find different compositions in the crystal phase and the liquid phase. And we take the average and we can get a point on a liquidus curve. So this gives us 1 point at each temperature. And then if I want to trace out this whole curve, I have to launch a whole bunch of other simulations at other temperatures and other compositions. It's very time consuming and painful, but you can automate this. And when we did that, we ended up with this coexistence curve for lithium chloride, potassium chloride. So the simulations are shown in gray. The experimental data is shown as dashed lines. This took a lot of the simulations, over 50 simulations. I'm embarrassed to say this was a couple 100,000 CPU hours to generate this. But we got this coexistence curve, and what we found was that on this side, the KCl side, we did a very good job of matching the experimental liquidus curve, but we did a poor job on the lithium chloride rich curve. And that's because we missed the pure lithium chloride melting point. We overestimated it by a considerable amount, whereas we got the potassium chloride melting point almost perfect. And this is with this rigid ion model. So we said there's got to be a better way to do this than that, and we'd like to learn more about the system anyway. So it turns out you can use a free energy based method to do the same kind of calculation, and it's much more efficient, but it's a little bit more complicated to implement. And in a nutshell, what we do is we start with a system that's either pure lithium chloride or pure potassium chloride. In this case, we can start at pure potassium chloride. And then we can selectively transform some of the potassium ions in the computer and gradually transform them into lithium ions. So we start with a potassium potential and we scale that potential by a parameter called lambda. And at lambda equals 0, this ion behaves like potassium. At lambda equals 1, it behaves like a lithium. And this is the scaling of that rigid, or that polarizable ion model potential. So what we can do is we can pick off some of these potassiums in our system and gradually turn them into transforming molecules. And we perform a range of simulations at different values of lambda. And we use a technique called multi-state Bennett's acceptance ratio to compute the free energy of moving from one value of lambda to the other. And so here you can see there's multiple simulations to go from 0 to lambda equals 1. And each one of these is for just 5% of the ions in the system. I can go ahead and then repeat that and identify another 5% and do that again and again and again. So this involves a lot of calculations, but overall I can get the free energy of changing potassium chloride into lithium chloride at different compositions. And when you do that, you get the Gibbs energy as a function, the excess Gibbs energy as a function of composition. And we also then get the enthalpy and the entropy, and then you automatically get the volume, the excess volume as well for free. And so what I'm doing is showing you the comparison here. And the very exciting result here is that compared to the experimental excess Gibbs energy, we are almost spot on with our model. The enthalpy is very good. The entropy, these are small numbers, is also quite good because we start here at pure potassium. The error propagation gets worse and worse and worse as we continue to do this transformation method. So we get higher error bars here at the pure lithium mole fraction version. And you can see we also kind of miss the volume, excess volume of mixing, but these are really small numbers. And so we're not so worried about that. We were glad that we got the Gibbs energy right. So from that, we can get the activity coefficient, and from that, we can trace out this liquidus curve, as I showed you before. So the red curve here is our prediction from this activity model, the free energy model that I just showed you. We fit our activity coefficients to a model, so we get a continuous curve now. And the gray points, again, are the direct coexistence methods. Now, because we used exactly the same potential, this polarizable ion model, we should get the same liquidus curve, and we do. So we're happy now. We believe that the method that we developed is accurate, but of course, we still miss the lithium chloride melting temperature, and so we miss the liquidus curve. We applied the same thing to the KCl MgCl2 region. This is now a little bit more complicated because in the middle region here, there's some additional solid phases, which we didn't account for. So it's only over here at the low MgCl2 or the high MgCl2 region where it's pure solids. We went ahead and did the calculation, and we got this red curve here. It agrees very nicely with, again, the pure KCl region, and we overestimate the magnesium chloride melting temperature. So our liquidus curve is also much higher than the experimental curve. So this tells us a couple things. One is that we have a nice method that's actually much more computationally efficient than the direct coexistence method. And it tells us something about the free energies involved, which is very helpful. It also tells us, and I won't show this, but if we adjusted these melting points and use the experimental melting temperature here, these curves match the experimental values almost perfectly. You can kind of see that if you just scaled everything, which tells us that we're getting the non-ideality of the liquid phase right with our model. All we're missing is the melting temperature of the pure LiCl and MgCl2. So about a fourth of the cost, we can get these coexistence curves. I would say we get good agreement when we have the right melting temperature, but when we don't, we are off. What we're currently doing is trying to develop better potentials than this polarizable ion model. That model was fit to liquid phase quantum calculations. And what we're doing is now developing a machine learning potential using both the liquid and the solid phases. And we think we can get more accurate values and then apply these techniques to map out even more accurate phase diagrams. And then the value of that, of course, is we can look at salts for which we don't know the liquidus curve, because we can parameterize these models using ab initio methods. So that's the first thing I wanted to, and the bulk of the talk I wanted to talk about with molten salts. Maybe I could stop and see if there's any questions there, and then the second half, I want to talk about electrolyte solutions. So I don't know if people have a question or if you want me to continue, I'll just go ahead.
All right, it looks like we do have a question. I made it so people can't unmute themselves, so let me
Okay.
get to them. Okay. John, go ahead.
Yeah, I had a question on so when you for the lithium chloride and the melting temperatures, was there not a reliable experimentally known melting temperature? Did you have to simulate that, or was it just
Yeah.
what is that
So
the
looking
case?
at this here, right?
Yeah.
No, there is a known lithium chloride melting
Uh-huh.
temperature, and this is it right here.
Yeah.
And the problem is that when we implement this polarizable ion model here,
Mhm.
this model, which was developed for these salts, if you calculate the melting point, you overestimate it. So if the
Okay.
model itself
The
doesn't
model
give you the right melting, it does perfect for KCl.
Okay.
It also does really well for sodium chloride, but it
Mhm.
doesn't do well for lithium chloride, or it doesn't do well for magnesium chloride. It gets the liquid phase non-ideality right, which is what I was trying to say. So, and it was
Yeah.
parameterized against the liquid phase. So what we think is that the model just is missing something, and it's not getting the solid phase right. So that's why we would like to get a better potential. And if we can get a potential that can get both the liquid and solid phase, we think we can match the experimental liquidus curve much better. Yeah.
Thank you.
But you need these methods to test these models, and people had not really been doing these kind of tests. They didn't know how well they would perform. And what we're discovering is that they have some drawbacks, and so we need to improve the quality of the models. Yeah, good question, John.
Thanks.
Trevor, did you have a question? I thought I saw your hand. Maybe not. Okay.
Sorry, I was
Okay.
struggling to get unmuted. Edward, I'm loving this talk. Thank you so much. I don't want to get off topic, but can you say something about how corrosive these materials are? The thought of liquid salts at 600 Kelvin
Yeah.
pouring around my nuclear reactor might make people a little nervous.
Excellent point. And that's one of the main thrusts of our EFRC is corrosion. And it's a big problem. So a lot of the folks at Idaho National Lab and Brookhaven are doing corrosion studies. We are trying to develop models right now that can simulate these salts next to the different alloys that they're looking at. And what is involved there is you need to go well beyond these sort of atomistic simulations. So we're looking at people who are doing phase field modeling, where we can calculate things like diffusion coefficients and some reactivities, and then they put these in phase field models and do the kind of bulk scale corrosion studies. But very good point. Corrosion is a huge problem with these things, and it's something that the center is trying to address.
Oh, Ryan?
Could you ask about the physical significance of the 1/r⁸ term in the potential?
Sure. So Ed, we have a question in the room. What is the physical significance of the 1/r⁸ term in your potential?
Okay, great question. If you these dispersion terms are really come about from dipole-dipole, induced dipole-dipole interactions. And when you calculate the distance dependence of those, the way that those are solved, it ends up being a series solution that goes like 1/r⁶ plus 1/r⁸ plus 1/r⁻ plus 1/r⁻12, etc. And people typically have truncated it at just 1/r⁶. And so the Leonard-Jones type potential is an example of that. The 1/r⁻12 repulsion has no physical significance. It's just a convenient mathematical operation to get something that's very repulsive. Something like an exponential term is much more physically realistic. What the Tosi-Fumai potential decided to do was to basically keep the second term in the series, the 1/r⁸. It's a little bit shorter ranged, but more importantly, it gives you a second parameter to fit your data. And so that's, I think, one of the main reasons why we've retained that. But that's the physical significance. Those distances are part of the series solution to that expansion.
Thanks.
That's a great question.
There are no other questions. I guess we'll let you keep going.
Okay, I'll go a little faster on this. You've seen all the tricks now. But the second point is if we want to also use solar and wind, this is growing rapidly. Both of them are growing, huge capacity increases. But of course, you need energy storage because wind doesn't blow and sun doesn't shine all the time. And 96% of our capacity for energy storage in the United States today looks like this. It's pumped hydro. And we have about 23 gigawatts of stored capacity. If you look at the kind of capacity of wind and solar, we're way bigger than that. So we need to put online a lot of storage capacity. And we've pretty much maxed out every place in the country that we can do something like this. You certainly can't do that around where I live. And probably you can't do that around where you live either. You have elevation, but no water. We have lots of water, but no elevation. So we need probably batteries. And so one of the ideas is to use large scale flow batteries. I think lithium ion batteries are not going to be cost competitive to store huge quantities of electricity. But these kind of things where you have just giant tanks of analytes and catholytes separated by a membrane, and you can just do a redox reaction, either pump in one direction or the other to charge or discharge. And you could couple these things with, say, solar arrays to store a lot of your energy. So I'm part of the Joint Center for Energy Storage Research team, which is a DOE hub headquartered at Argonne in Chicago. You can see lots and lots of partners, 12 universities, 6 national labs, over 180 researchers. And J. Caesar's has been going for about 8 years now, or yeah, about 7 years now. And our goal is really to design batteries from the ground up, looking at crystals, atoms, and molecules, and trying to figure out how we can put them together. And flow batteries are one of the things that we're looking at, and what kind of electrolytes we need. And so our role has been to study electrolytes in these systems. Again, we're using these molecular simulation techniques. There are lots and lots of experimental colleagues who can do things like X-ray scattering, diffusion coefficients with NMR. They can do all kinds of DSC, neutron scattering, viscosities. And so we try to do validation of our models, try to develop some molecular level insights, and ultimately make predictions. And this is the kind of potential that we use now. It's not like that ion potential I showed, but this one has intramolecular terms because the solvents that we're looking at are molecular species, they're not just spheres. But the same kind of things we use, molecular dynamics and Monte Carlo. So we got very excited when we saw this work that came out. This was a groundbreaking paper from Kang Zhu's group at Army Research Lab that was in Science about 6 years ago, where they discovered or published about the so-called water and salt electrolytes. And what they found was that if they took lithium bistrifluamide, TFSI is a fairly large anion that has fluorines, sulfurs, nitrogen, oxygens in it, and they got 21 molal concentrations of this in water, they saw something really interesting. So if you're at low concentrations, they saw electrochemical windows that were about 2 volts. The electrochemical window of pure water is about 1.2 volts. So they saw an increase in the electrochemical window, but they could see very high electrochemical windows when they got very high concentrations. So they were seeing electrochemical windows of almost 3 volts for these so-called water and salt electrolytes. And that's really amazing because you need high voltage batteries to have high capacities. You'd love to have an aqueous battery because they're cheap, and that's what we need for flow batteries. They're safer than having organics that are combustible. So this is fantastic. And so the question that they came to us with was, well, why are these so stable? And also they saw very high lithium transference numbers in these systems. So you got very good performance. And what's going on there? Why is that happening? So we have been carrying out simulations of these systems Some early work postulated, or not even so early, just recent work about a year ago from J. Caesar people, had postulated that when you get very high concentrations, you start to form these special domains of sort of water channels, which are shown as green here, and then anion globs or aggregates that are shown as blue here with lithium. And somehow that this is, they weren't sure why, but this stabilizes the lithium. And these water channels provided for rapid diffusion of the, or conduction of the lithium ions. And they had some evidence from some small angle X-ray scattering shown here in blue. This is an inverse distance. So if you look at this, this is the opposite of the Fourier transform of that radial distribution function I showed you for molten salts. This peak here is sort of a long range order that kind of corresponds what they thought to this length scales of these sort of structures. And then they see another weak shoulder here. And the simulations saw also these two type of peaks. So that was some indication that maybe this is the right picture. And they also were able to get transference numbers that agree pretty well with NMR. When we looked at this, we were a little bit worried about this because this also looks like what happens when you run a molecular dynamics simulation above the solubility limit and you start to see phase separation. But of course, there's no gravity in a molecular simulation, so you don't see an interface form, but you do see these sort of domains. So this also could be just the solubility limit of these systems. And we know that 21 molal is close to the solubility limit anyway. So we partnered with Andrei Tokmakov's group at the University of Chicago, who was doing some FTIR measurements. And we did some simulations, and he looked at basically the structure and the vibrational frequency of these TFSI anions. So this is what a TFSI anion looks like. And I'll point you to this figure over here. What they could do from their infrared spectroscopy was look at the number of acceptors to the TFSI anion. So basically what's coordinating with the TFSI anion as a function of the concentration. Now they're plotting this in molarity, but over here at 5, this is up to 21 molality. And what they find is that the number of acceptors of the TFSI steadily goes up. This is with water interacting with TFSI as the concentration goes up. So we're seeing very strong interactions and increasing in the number of acceptors. And our simulations show exactly the same type of behavior. They also could get some sort of time values that we are not able to get because we're just using classical simulations. So this was the first indication that our simulations are consistent with their FTIR. And we went further and did some measurements or simulations and compared our densities. So this is the overall density of the system versus LI-TFSI concentration at different temperatures. The open symbols are our calculation, or sorry, the experiments, and the solid symbols are our simulations. And we're quantitative, we're within 1% of the densities for all of these. We then also looked at X-ray scattering, but now we looked at a much broader range than just the very low Q peak that was looked at earlier. And here's the overall X-ray scattering results. The calculations are red, the experiments are blue. And this is really good agreement. We get those two peaks that they saw at the low Q region. Here's the lowest Q peak, and here's that little shoulder, but we also get the higher Q values quite accurately. And if you blow up the low peak region, we also get the concentration dependence of this. What you see is that the emergence of this second shoulder peak comes in as the concentration goes up. These are our calculations. These are the experiments. The agreement is remarkably good here. So we think we're getting the structure of the liquid accurately. We're also getting the densities right. And we see fundamentally a different picture than what was observed earlier. Instead of seeing these domains of water channels, we see, unfortunately, kind of a more boring picture. What we see is that at low concentrations, you see a regular hydrogen bond network of water. That's what's shown here in red. And then we see interspersed some lithium TFSI. That's what's shown here in these blobs at low concentration. As you raise the concentration, the blob concentration increases, and then you start to break up this water hydrogen bond network, and you start to form a network of lithium TFSI, and that makes perfect sense, but you're getting a higher concentration. But it's a more or less smooth transition. We don't see these domains forming. We don't see water channels, we just see a breakup of the water itself. From FTIR, they could back out the concentration of what they're calling systems where there's two anions associating with each other. That's the blue curves. One water and one anion, that's green, and then two waters. And by integrating these, they can get the concentration or the probability of these different systems. And so what we're plotting here is the probability of two water in red, one water, one anion, or two anions in blue versus lithium TFSI concentration. And the solid symbols are calculations, solid lines, and the dashed are experiments. And you can see that the simulations are matching the experiments very well. Where you see two water, where you see water-water interactions, those are very high probability at low concentrations, and that's broken up as you get to high concentrations, just like what we see here, but it's a continuous curve. Two anions together forming these sort of clumps, you hardly ever see that at low concentrations. That's typical of this picture. And then you see a steady, continuous rise in these two anions, a gradual transition. And then for one water, one anion, where you start to see pairing of the waters and the anions, you don't see much of that when you have no water, and you don't see much of that, when you have no water or when you have no lithium TFSI, and you see a maximum at intermediate concentrations, and that's exactly what we see. So we also showed that you can get the dynamics of the system very accurately with our model. We can calculate the viscosities, and we get quantitative agreement with experiments. We get quantitative agreement with the diffusivities of lithium, TFSI, and water with this model. And we also get the ionic conductivity and the transference numbers. So here's ionic conductivity as a function of concentration. The experiments are shown here in these blue and pink curves. They see a maximum at 5 molal, and then it drops down. We see the same maximum at 5 molal, but we predict higher conductivities than what's observed experimentally, but we still see this maximum. What's causing this maximum is that as you increase the number of charge carriers, the conductivity goes up, but it doesn't continue to go up, because also as you increase the number of charge carriers, the viscosity goes up. And so the mobility starts to go down. And there's a competition between those two. At 5 molal, it reaches a maximum. And even though you have more charge carriers at 10 and 20 molal, the viscosity wins. And so the overall conductivity goes down. However, the lithium transference number continues to go up. That's seen experimentally. It's also seen in our simulations. And we don't need water channels to explain this. We can explain it by the fact that the reason that we see an increase in the transference number is that the diffusivity of TFSI drops faster than the diffusivity of lithium. And that's because TFSI is forming a network here and slowing down. And so the transference number is determined from the ratio of the diffusion of lithium to the sum of the lithium and TFSI diffusivity. If this goes down, by definition, the transference number goes up. So we think we understand the system really well now. And we're continuing to look at now other systems. I'll quickly show you some very recent work that we're doing of looking now at multivalent systems, zinc instead of lithium in these water and salt electrolytes. We have a paper that just came out in Angevin, and it was stimulated by some work in Nature Materials that came out in 2018. They saw that as they added a supporting salt, so now a phosphonium TFSI, this is an old ionic liquid that we've looked at for many years. If they added that to a zinc system that's at 4 molal aqueous zinc TFSI, they saw an increase in the Coulombic efficiency. They saw very high electrochemical windows, and they also saw that the cycling time was extremely high, much higher in thousands of hours compared to other zinc-based systems. So this magic phosphonium component gave them much better performance in many different ways. And so again, they asked us to see if we could simulate that to explain what's going on. We looked at a simulation where we had a very large system with model graphene electrodes. We put in the phosphonium or phosphonium with ether groups. And to make a long story short, what we learned is that these hydrophobic phosphoniums will localize near the electrode surface and drive away the water. So at the positive cathode, you can see here the water is driven away from the interface where it will localize at the interface with the negative potential. And you can see snapshots of where this is going. And the ether containing phosphonium does the best job of driving the water away. And we think that this helps form an SEI layer at the interface. And that's our hypothesis. There's some experimental evidence that suggests that that's exactly what's going on. So now we're looking at other supporting salts or other additives that can change the concentration of different species near the interface and play games with the conductivity. So I'll try to finish here. I think I'm about out of time. I hope I've convinced you we can simulate these molten salts fairly accurately and get structural as well as dynamic properties and phase diagrams. We need to improve the quality of the potentials. They haven't been looked at for a long time, and we're doing that with some machine learning methods. And then we've applied our methods also to look at these highly concentrated water and salt electrolytes. They have many benefits, and we think we can look at other multivalent systems and look at other supporting salts. So we've really kind of come full circle from the early 1970s, where molten salts were the first systems being looked at. And now we're looking at some very sophisticated simulations that those folks could really only dream about doing with today's methods and computers. So I want to acknowledge the molten salt work. We collaborate very closely with Claudio Margulis and Slava Branchev at Oak Ridge and their group. So this is the MC Theory group. This is a picture of my group. And all the work I showed you was done by these three folks: Yang Zhang, who's a research scientist in my group, Haimeng Wang is a graduate student, and Ryan DeFever is a postdoc who just left because he got a real job. And the DOE has supported all this work. So I hope that that was maybe understandable. And if folks have questions about this part or anything else, if there's still time, I'd be happy to answer them. Thanks very much.
Great, great. Thank you. That was really interesting. So if people have questions, please raise your hand. I'm going to kick things off. I have a question for you. So my group has spent some time looking at not really similar eutectic systems, but still looking at eutectic phase diagrams and trying to predict them. And one thing that's really been bugging me is the ability to predict solid solution behavior,
Yes.
either from thermodynamics or from molecular dynamics. Have you tackled that? Do you have an approach that allows you to get at that line?
Yeah, that's a great question, Garrick. And what we've done here is we've assumed the method that we use for this free energy based method assumes a pure solid phase for both of them. So we're assuming pure KCl over here and pure lithium chloride over here. And we do that because we have to develop a reference chemical potential to that phase. And we can get that by knowing the pure melting temperature.
Yeah.
And we have methods to calculate them. I didn't get into that, but we have a free energy method to calculate melting points. With a solid solution, which is exactly what we saw, that's why we kind of skipped over this. We see these solid solutions in mag chloride. We just gave up, we punted, and we only looked at the region of the phase diagram where we have pure magnesium chloride or pure potassium chloride. I think one way to do this, and if we wanted to apply these methods, would be we'd first of all need to know what the crystal structure of these solid solutions is. And then we could go ahead and, just like we did for the pure crystal phase, calculate essentially the melting temperature, and from that we can get a free energy, and then use this to map out these different diagrams here. But that gets all of a sudden an order of magnitude more complicated than what we're trying to do here. And so we haven't done that yet. That's a really hard problem.
Yeah, absolutely. I mean, it's
I don't know of another way to do it, but if you know of a better way, I don't really know that. I don't really even want to do that. That's terrifies me.
Yeah, no, I understand exactly what you're saying. One more time, if you want to ask a question, please raise your hand and I will unmute you or ask you to unmute yourself. I have one more question, so I'll ask that. There are no hands up. When you were talking about the conductivities towards the end, you had conductivities sub NE, which I assume is Nernst-Einstein. And then you had some other ones that were sub just E by itself. Are you approaching calculating conductivities in a different way? I guess my question is, how are you calculating conductivities from the?
Yeah. Okay. So are you talking about the molten salt or for the it doesn't really matter. We do the same. We do it both ways. We use an Einstein method to calculate them, and then we also calculate them using a Nernst-Einstein. So the rigorous way where we include cross correlations, and then we do it with just using the diffusion coefficients. And the nice thing about that is you get from that, you can decompose. If you do the rigorous conductivity, you can decompose the cross contributions to the overall conductivity. And what you see is that, for example, you'll get anti-correlation of, say, lithium with chloride that serves to reduce the overall conductivity. But as you know, that's a more expensive calculation to do. But we like to do that if we can afford to do that, because it gives you a lot more insight into what's going on.
Yeah, makes sense. And it's got to be important for these really concentrated.
Yeah, exactly. For dilute systems, you might get away with it by assuming that these things are not correlated. But certainly at high concentrations, you're going to have correlated motion, and we observe that.
Okay. I have more questions, but I think maybe I'll send you an email.
Okay, that sounds great. I'd love to chat some more.
Thank you once again for a really interesting talk. I found it really inspiring. Let's thank Ed one more time.
Great. Thank you very much. I appreciate the opportunity to speak with you. And if anyone has any questions, you can find me, send me a note. I'd be happy to chat with you.
Wonderful. Thanks again, Ed. I know it's relatively late there, so thank you for giving up your evening to chat with us.
No problem at all. No problem at all. Thanks.
Rest of
I
your
got
day.
out of doing dishes tonight, so that was great.
It was worth something.
Yep, exactly.
Thanks
Okay.
again. Have a good night.
Thank you. Bye-bye.
Bye.